Welcome back. This is the second part of a two-part series in technology and mathematics, and this part will deal with visualizing with technology tools in mathematics. The first session dealt with school math, a little bit of standards, and how that connects to real-world math or doesn't, especially in a 3D world. Now we're going to look at we're going to add to those topics and think about how science and math have worked together to really create a new kind of math to do a new kind of science. We'll look at the math tools to pursue those studies and ways of thinking mathematically. So we left with this image of a 3D cube as though that's a big important thing to study. That's dirt simple. What in the world is there in our 3D world that is that simple? We'll want to analyze anything in our 3D world mathematically, and there are tools to do that. So in Santa Lupo High School, back in 2009, a student designed this shape in a 3D modeling program where the student is creating and manipulating, managing 3D shapes using mathematical and geometric tools. And then, as we see with the John Paul II Secondary School student, you can then, with the same system, convert that to a photorealistic, what's called a rendering. These are the applications of modern mathematics, not even getting into science. Now, do you have to be a high school student to learn this? Well, the little girl over here, who happens to be my niece, is age 7. She's using a program called Blender, which is the entry to 3D modeling, 3D animation, and 3D printing. So with that program, we can create 3D game characters. We are using all sorts of mathematical terms, geometrical constructs. This is modern math. If you master this, you can create 3D renderings that look like a photograph or a painting. But this girl's face on the right was actually created mathematically using modern mathematics, not school math. Modern mathematics excels at the shape and line and texture and color that you find in nature, rather than the straight line artificial sort of order that you find in school mathematics. So the 7-year-old wanted to learn the 3D software so she could learn 3D printing. So now you can design shoes in 3D. You can print a car body with a 3D printer. This wrench, it happens to be printed in plastic. It could be printed in metal. But the most interesting part is that there are 3 interlocking parts. Before 3D printing, those parts were machined and created separately and then assembled. With 3D printing, they are printed together. In other words, the interlocking parts are printed in one print, and the pieces inside automatically move. They don't have to be connected to the outside. So this thumb wheel is perfectly mobile. This Mobius strip was printed in glass. So 3D printing is what the 7-year-old will live with when she grows up. So this polecat unmanned aircraft with a 90-foot wing spread was printed in 2006 with 4 tons of plastic. Now, the 3D printing world has grown, so now we have a company, Contour Crafting, that will be able to print your house on site in 24 hours. So it's new math, 3D math, that helps do this stuff as opposed to primarily school math. Now, the National Council of Teachers of Mathematics in 1989, released their Standards for Mathematics. That was the first instance of academic standards. And it was pretty cool because they realized that kids weren't learning and remembering math. So their solution was, gee, we teach too many different topics. So they wanted to teach fewer topics in greater depth so that kids would learn more. That's actually the mantra of a 3-year plan for Singapore that they learned from NCTM, from their 1989 system. So how do you teach less? You have to take something out of the curriculum, don't you? So the mathematics teachers looked ahead and thought, we can tell two things that we know will not be as important in the future. One is fractions, the other is customary measurement, because we are in a metric world, like it or not. And the world doesn't measure things in inches and miles and pounds. So they would have a corresponding emphasis with decimals and metric measure. Decimals and metric measure reinforce the mathematics that are already taught with our decimal system of manipulating numbers. It's estimated that our students in the U.S. lose about 1 year of mathematics instruction compared to the rest of the world, solely because they have to learn and relearn these outdated topics compared to kids in the rest of the world that simply don't have to deal with complex fractions and customary measurement. A perfect example is the spreadsheet, the way that everyone in the real world does math. If you create a pie chart, that's how our kids are taught fractions, isn't it? But this will be shown with percentages, not fractions. Try entering a fraction in a spreadsheet. You enter it as a division problem, it converts it instantly to a decimal. We are already in a decimal metric world. Our schools just haven't caught up to that. But what's another reason why we feel we're not good at math? About a third of Americans think that they're simply not good at math, according to a 2015 study. And why not? It's not just Americans. So engineers in Brazil, India, Egypt, China, all around the world are highly trained at math, but they can't apply what they've learned to any new or novel situation. Their math is fixed because of how they were taught. One reason is that no matter how closely we look, we can't find a math brain. We have a language brain here and here for understanding and producing language. That's how kids learn language on their own in 2 years. We have a part of our brain that deals with muscle control. So kids on their own learn to walk and manipulate things. We have a visual brain that allows kids to learn what things are, identify things, and make sense of their visual brain. We have no mathematics brain. So all of the math that we have learned has been by constructing that area in our brain, a complex process. This is a process that can be aided by tactile manipulation, such as is done in Montessori schools, and in later years, visual interpretations of numerical math. So the Cadillac of of math visualization is Wolfram Mathematica. So here we can take a group of numbers and do a bar graph, very simple things, or something like, gee, here are a few sine waves of different frequency, and we can graph them easily. But we can graph any three-dimensional equation. We can graph 3D objects that are beyond squares. We can do fractal geometry, all sorts of things. These things are impossible to do in paper and pencil. They need a computer. They're part of modern mathematics. that you need technology tools to use? Well, Mathematica is complex and expensive. For many applications, a program called MatLab is used. Here's MatLab. So this is sort of the program that you would write to create this 3D graphical output. And it's complex. You have to learn it. MATLAB is also a little expensive. So the SAGE program is a free analog to MATLAB. If you want to learn this stuff, how math is used in the real world, learn MATLAB or SAGE. If you want to do statistical processes analysis, run statistical tests, SPSS is the typical standard. Again, that's expensive. You have it if you're in college. When you graduate, you don't. There is a program that will also run statistical tests and do some more things too, called R. This is a sample of an R screen. So here is the setup for the statistical test, and you can get just a huge variety of output through programs like R. School math doesn't teach you this stuff. This is the way that mathematics makes powerful impact in the world. If you know these things, you can get a good job. You already know about Gapminder, Gapminder's motion charts, and we're typically graphing two variables, like we might graph an x and a y variable. But with Gapminder, we can also, by the color, figure out what continent it is, so that's a third variable. The size of the bubble is the population, that's a fourth variable. And there is a timeline so that we can run this through the years, so time becomes a fifth variable. These are the tools to allow us to chart and visualize at simultaneously 5 changing variables. That's the current standard, and our schools need to use technology tools to help kids learn. One way to think about this is the words of the mathematical and computer scientist, epistemologist Seymour Papert. So he says the role of the teacher is to create the conditions for invention rather than provide ready-made knowledge. In other words, don't just give kids formulas, give them tools. Again, his words of wisdom. In his view, a computer is a device to think with. And this is a wonderful way for us to think more deeply, especially in mathematics.